Hello everyone, this is Professor Pawan again, and in this video I am going to derive the second part of the bending equation, that is the relationship between bending moment and radius of curvature. And for that I have drawn this particular diagram here. Now this diagram gives us a beam here, and let this be the neutral axis of the beam, this axis passing here, and let us consider a very small section of area delta A, which is at a distance of y from the neutral axis. Okay. Now this is very small elemental area, as I said. Now we know that stress on this element, stress on this small element, I am talking about this small element. Okay. What will it be? It will be equal to, from the previous derivation, we can say that sigma is equal to E by R into y. Okay. Sigma is equal to E by R into y. Now, force on this element, the force on this element is nothing but the stress into the area, because stress is forced by the resisting force by area, and hence force becomes stress into area. We have got the expression for stress. So, what will be force then into area? So, this becomes, this is equal to E by R into y into the area of the small element is delta A. This is the force on the element. Now, similarly, moment of this force, will be equal to the force into the perpendicular distance, and we know that the perpendicular distance from the neutral axis is y, and hence this moment becomes E by R into, I will write y square into delta A. This extra y is due to this distance. Since moment is force into distance, that y I have made it y square here. Okay, so this is the moment about neutral axis with respect to area A. Okay. Now, algebraic sum of all the moments about the neutral axis, I am repeating once again, listen carefully. The algebraic sum of all the moments of the neutral axis, let it be m, okay, and that will be equal to summation of individual moments of all small areas. That is, individual moment is this. So, this will be summation of this individual moments, which is E by R into y square into delta A. Okay. Or I can take this E by R outside into the summation of y square delta A. But from the elementary mechanics, we know that y square delta A is the area moment of inertia about the neutral axis. This y square delta A is area moment of inertia. So, simply I can write this m is equal to E by R into I. Instead of y square delta A, I am writing I, because I is the area moment of inertia. Okay. So, here what I can write now implies m by I is equal to E by R. Now, considering the previous equation and the present equation, what we can write? We can combine the previous and the present equation to form the whole bending equation. Now, what does that say? M by I is equal to sigma by y is equal to E by R. So, this is the total bending equation, okay, which consists of two parts, and the two parts we just derived just now, okay, where m is the bending moment in terms of Newton mm, I is here I is area moment of inertia whose unit is mm power 4. Sigma is the normal stresses or bending stresses whose unit is Newton per mm square. Y is the distance from the neutral axis measured in mm. E is Young's modulus, which again is in Newton per mm square, and R is the radius of curvature measured in mm. So this is the bending equation. Now we will discuss some of the other parameters which are very important with respect to the theory of bending. Okay. And one among such is this thing called as section modulus. Section modulus. Okay. It's called as section modulus. Okay. We'll discuss what is section modulus now. We know that from bending equation we know m by I is equal to sigma by y. I'm only writing the half part of it. So what I can write, sigma will be equal to m by I into y. Sigma I can write it as m by I into y. Now this shows that for a given cross section the bending stress will be maximum where this y is maximum, and if y is minimum, sigma will be minimum. Okay. So this is one of the very important things, and based on this what I can write let us say if sigma is equal to the maximum stress or allowable or permissible stress or basically the maximum stress, then sigma d will be equal to, if I write it here, it will become m by I, and when will it be maximum? If y is equal to y max. Okay. And similarly I can write m. Now what will m become? M will become I by y max into sigma d. It will become I by y max into sigma d. Now this I by y max, this parameter we call it as section modulus, that is ratio of area moment of inertia and the maximum distance, or basically the distance of outer fiber from the neutral axis. This we call it as section modulus, or I'll write it as m is equal to z into sigma d, where z is equal to section modulus. Z is section modulus. Okay. So this is the basic concept of the section modulus. Okay. So fine. Thank you. We'll solve the problems in the next video. Thank you very much.